Good afternoon and good evening, everybody. It is great to see how many of you have joined us here today, and welcome to this webinar hosted today by TATA ELXSI. The speaker today is Sajan Unnikrishnan, Senior Technical Architect at TATA ELXSI. And also joining us today for the Q&A session from TATA ELXSI is Mr. Ajith, Mrs. Sujata, and Mr. Sandeep. Sajan has a master's in software and systems and is a subject matter expert in an area of model-based system engineering. He has over 16 years of rich experience across rail, automotive, and aerospace. Currently, his focus is in facilitating clients to deploying model-based system engineering techniques at TATA ELXSI. We do encourage you to ask plenty of questions today. At any point during the webinar, please type in your questions into the Q&A box you will find at the bottom of the screen. At the end of the presentation, we will present your questions and answer as many as possible. It is an absolute pleasure to have Sajan with us today, and I would like to warmly welcome him now to take control and begin the session.
Thank you, Martin. It's my pleasure to address this esteemed audience that we have with us today. So over the next 40 to 45 minutes, I hope to summarize the relevance of MBSE with respect to rolling stock development. There shall be summary of various challenges that can be addressed by MBSE, methods for applying MBSE, and the benefits gained by it. Before getting on to the topic though, let me give you a brief 2-slide introduction to TATA ELXSI and our offering with respect to rolling stock development. TATA ELXSI is an integrated design, engineering, and technology-based company. We are headquartered in Bangalore. We do consumer research, technology consulting, product design, development, testing for various industry sectors like transportation, broadcast, communication, medical, and more. Our core team of 7,000 engineers and technologists work from different locations across the globe and service our global clients. Coming to transportation, we have been working in transportation for the last 20 years, and we bring together a world-class team covering various aspects like the embedded, mechanical, testing, AI, analytics, IoT. Also, we do have an award-winning HMI team. Within the transportation segment, we focus on rail, automotive, FMCE, that's farming, mining, construction equipment, and aerospace. So we work with leading OEMs and suppliers like R&D, design, product engineering, right from architecture to the launch and beyond. TATA ELXSI has promising technologies and innovations that can potentially transform the rail industry. We intend to reimagine product and services through design thinking and application of various digital technologies. Now, this slide shares the full picture of our services for development of rolling stock and systems. We engage with rail OEMs right from the pre-bid phase and support them till the first unit goes live. At a train level, we help the OEMs with operability engineering. Now, this is done by working with OEMs as well as operators to define the operability requirements of the project. We also do the requirement management from train level all the way down to the component level. We also undertake human factor analysis, such as design of overall driver cab, glare assessment for lighting aspects within the driver cab, and so on. Also, our industry design team does the concepts, styling for the driver cab and saloon. Next, at a functional level or the systems level, we engage with OEMs in defining the architecture of the specific project. We undertake functional modeling and simulation of the train functions. This is to enable left shift of the validation. And this is something that I'll be covering in today's session as well. We also add value in the driver cab HMI prototyping to align the interfaces with various stakeholders before actual development begins. Moving on to the component and subsystem level, we undertake model-based development of onboard electronic systems such as the TCMS and other subsystems, and perform independent V&V, software quality assurance, component and subsystem validation using hills and automated test equipments. In addition to all this, we do mechanical engineering. So on mechanical engineering side, we provide services for physical installation and integration of the cab and saloon for both the interiors as well as the exteriors. Now coming to the topic of the day. So as all of you might have already guessed, I would be advocating for model-based approach to system engineering as an enhanced way of performing system engineering. Now, why do we try to improve something? There should be a business case for that, right? Let me start with setting a business case first. Now, system engineering itself is the most critical and say high impact activity when it comes to rolling stock development. As builders of complex system of systems, I'm sure all of you agree that we should constantly endeavor for improvement. You might have a process in place, right? But with very small improvements in the process or the method or the tool in system engineering, we can start realizing benefits. Now, some of the direct benefits that you can get are, say, reduced time to market because of perfection, reduced cost because less errors are there, reduced defects, and you'll be able to handle multiple vehicle variants. Now, that's a direct benefits in the business level. And the cascading benefits are you are more confident with the bidding process, the acceptance level of the product is higher, and overall there's a more collaborative ecosystem between the three main parties, that is rail operators, rolling stock manufacturers, and the tier one suppliers. Now the question that will be arising in your mind is, will MBSE achieve all these benefits? And the answer is yes. I will try to give you an encapsulated view of how all this can be achieved through MBSE. So in previous slide, you saw benefits that business would like to see. However, for a system engineering practitioner's point of view, you would resonate more from the day-to-day challenges that are faced. Let us discuss some of the challenges. I know there are so many challenges that can be tackled by improvement of system engineering process, but let's prioritize and pick up three categories. So the first one which is being listed here is issues being unearthed late in life cycle. So how late it could be, say as late as identifying issues in the stages or during the on-train testing. Now failure at this kind of a stage is actually going to affect the deadline. It's going to cause penalties. Why does this happen? It happens because either the requirements is incomplete or inconsistent. At the design level, the interfaces have gaps, it's not correct, or simply because there's such a lot of complex interdependencies between the systems, which is not well understood at an early stage. The second issue that I would like to discuss today is on building platforms ground up. See, there's a methodology called product line engineering or product platform based engineering, where maximum reuse is done from a platform perspective. So for every project, there's just a change is done. I'm sure all of you might have a product line engineering based philosophy already, but is the reuse as effective as it should be? Reuse is only possible if there's a proper process to enable reuse. Now, there should be a process where you can pick and choose elements for reuse. And that's where MBSE comes in. And a third case is requirement cascading and collaboration scheme. Now, it's easy to say that we can collaborate well, but think about how many different stakeholders are there. You've got collaborations from right from operator level to the train builder to the tier one. Within the train builder itself, you have various roles, the chief engineers, the vehicle testing team, building block owners, functional team, safety team, vehicle engineering team. There's so many levels of people. And there's so much cascading of requirement that's happening between these levels. Now that means that there should be a better methods for collaboration so that the information is not lost. Now these are challenges. While we try to address these issues, it will also help us manage one of the expectation conundrum. See, today the rail is getting more and more complex. So the complexity of rail is increasing. Naturally, what you would expect is that time to market should also increase. Unfortunately, the expectation is that time to market is going to reduce. So that means we need to have a technique to address this conundrum as well. So I think with this first slide where I put out the business benefits and the second slide where I said what are the challenges from a practitioner's point of view, I think we are ready to discuss on the topic of model-based system engineering. So MBSE, the standard definition of MBSE says that we use models as the primary means of exchange of information rather than document-based information. Now, in the past, what used to happen is textual artifacts were being exchanged, or documents with ad hoc diagrams were being exchanged. The idea currently is that you should have models as a primary means of exchange. Now, models should be such that everybody should understand. So there should also be a need for a formalized way of communication. So model as a formalized way of communication is the future. Next, let's see where do we apply MBAC. What is captured here is a typical V cycle. So let's take an example of a new metro project. OEM and operators sit together to collate the operational mode scenarios, and that's where the first one item comes there, the operational requirements. Then OEM has to classify this into train functions. We call them functional blocks or building blocks or systems. Thereafter, it goes into software and subsystem levels. In this cascading process, there will be different aspects like safety criticality handling, cell level handling. And so that's all comes on the left side. On the right side, what comes is all the testing activities. So you have software level testing, Hills level testing, testing on a network train, network acceptance and homologation testing finally. Now, at what stage would you like to find the issues? Earlier the better, right? So if you see the dollar symbol here indicates that the later you find issues, the more money you have to spend on the rework. So we would like to find the issues earlier. So try to do MBSC or the modeling or try to make things systematic early in the life cycle. This V cycle that's shown here is actually taking an example of a software V after the systems path. Now, it doesn't mean that system modeling can be done only for the software or electrical or interface part. It can be applied for hardware or mechanical. The idea of modeling is actually agnostic to the downstream implementation. The other aspect you see on the left side is that there's a part captured as model-based development. I would like to take it as a separate substream and a separate topic where aspects of how do we model the software better, how do we generate code out of it, and all those should be addressed. So I've created a boundary on model-based system engineering, topic that we are going to discuss today. Okay, all said well. Now let's see how to create an approach for model-based system engineering. Is there a golden approach that I can share with you today? So the answer is the golden approach lies in trying to binding three forces. That's what is our philosophy. The forces are the structure, the behavior, and the requirements. These needs to be bound together very well. Now, what do you mean by this? Structure. If you take train, there's a structural aspect to it. Train consists of doors, the HVAC, TCMS, propulsion. There are a lot of other, say, electronic units inside that. Now, the structure aspects is there if you go one level down also. If you take the HVAC system in itself, it has structural elements like the compressor, the filter, the condenser. Now, you take the behavior. Behavior is there at a train level, where when a passenger alights the train, what happens? When a driver enters the cabin, what happens? There's also behavior within the between systems itself. What does TCMS do on a particular condition? What does it publish to doors and so on? And the requirements are also there at all these levels. There's operational level requirements, there are requirements at say the functional level and subsystem level. So the point is structure, behavior, requirements are omnipresent. It is there everywhere. The point is to discover them and then bind them closely and connectedly, such a way that the moment you change the structure, you should be able to point out which behavior will it affect, or if you have a change in requirement, what behavior and structure gets impacted. If you are able to bind these structure, behavior, and requirements correctly, it's going to make MBSC work for you. The modeling language for doing these models, I'm going to walk you through with SysML as an example today. That's because that's what we prefer. And the international OMG group, Object Manager group, has advocated for that. But some of our customers do prefer other languages like IEC 61131. 3, that is PLC based, more of an implementation language, but it can always be adapted to system level. But irrespective of what the language is, please keep in mind the idea of binding these three forces together. Okay, to get a flavor of the diagrams or what is systemal diagrams and what is structure, I will go through some examples. So the first example here is that structural modeling. Okay, block definition diagram of a brake system is shown here. So what this diagram gives you is a hierarchical view of train and its components. What are the different, there are different connectors like composition, aggregation, generalization, and so on, to show the relationship in a hierarchical fashion between systems and its inner elements. Please note, I will give you a quick walkthrough of the systemal diagrams. It's not a tutorial, right? So to understand the flavor of what is, I hope you're able to get the idea of what structural modeling is from this. Another idea of structural modeling is the internal block diagram. Okay, so here's an HVAC system. And what you are seeing through HVAC system here is that there are various blocks and there are various messages being exchanged between these blocks. So, messages like fresh air, circulated air, you're seeing that, right? So these are, so this, unlike the previous structural diagram, here you have block elements and their interdependencies in terms of messages. Now, as you see here, the example is using very high level messages like fresh air, circulated air. But downstream, this could be used for probably mentioning a CAN signal, okay? Or on a mechanical world, I could use, say, a pressure gauge as an input signal. So irrespective of what type of implementation you are doing, you could adapt this diagram. Next is an example of a behavioral modeling diagram. So use case diagram is a form of one, say, early behavior, where you are trying to set the context of the system. So here it's a door system, and there are a few actors which are outside the box are interacting with the door for the use cases mentioned in the door. So this is the kind of diagram that you would use in your very first meeting with say, between the OEMs and operators to chalk out the requirements probably. Next, what you see is an activity diagram for a horn operation here. And here you are seeing that the sequence of operations, there's a decision box, and there are alternate flows. What you're seeing is a vertical split that is called swim lanes. So to define the different parts, responsibilities of what a driver is doing and what a trainer is doing. But the important point I want to emphasize here is the decision box as an element. When you traditionally write requirements, you tend to think in one flow, that is the positive or the sunny day scenarios. But when you have using a diagram like activity diagram with decision box, at every stage you are thinking of a decision. What happens if that happens? What happens if this doesn't happen, and so on. So both the sunny day as well as rainy day scenarios are well captured in a diagram like activity diagram. Next systemal example I would like to take is a sequence diagram of HVAC. Now here you see a lifeline of various systems and the messages that is being exchanged between them. And there's a timeline in which the messages are being exchanged. The idea that this conveys is that this is not an early behavior like the previous case. Here, actually, we have already defined the structural elements. Those lifelines are the structural elements. So once you have some part of the structure, you're trying to define what are the exchanges between the structural elements. We can adapt this for different layers. Now, I've shown this example with probably a HVAC and a detailed messages. But at a high level, if you want to look at a train level, I could use it for example, what happens when a train enters into service, when it's in a running service, when it's at the station, when it gets into the exit from a station, when it's in a depot operation. So scenarios can be modeled for each of these. Next diagram is a state diagram, and this is a state diagram of a wiper system. And it shows various states and the transition condition between them. Again, this also can be adapted all the way to a train level. Say in a train level, you have states like normal state, restricted state, degraded state, emergency, maintenance, rescue mode, and so on. So we can adapt these diagrams. So with this, I would switch to the next topic. That is, you got a flavor of a systemal diagram, the structure and behavior. If you choose a different modeling language also, just you need to see that these elements are there. Now I'll show you through, I'll walk you through a video that shows that these diagrams not only are going to be interlinked, so we have interlinked them, and we are also going to animate them. That means these diagrams can be made dynamic. So what you see in the video now is on the right side is a state diagram, and what you see on the left, that is the train door operation. So there are various options that driver has, which is on the top of the door, where he can say enable or disable the door or open or close himself. There's an option to set the obstacle as well. On the right, you have options that a passenger chooses. Now, and with various states being played out on the right, you have seen a more intuitive visualization of it. So what it means is that the modeling is not just for the engineers who are very proficient in SysML. You can actually use it for visualization, and it could be a method in which OEMs and operators can sit together and agree on a feature. So this is like a virtual operation modeling. The second point I would like to show you is that these diagrams are, there's no logic on the visualization side. The entire logic is from the right side, that is from the state diagram. So if tomorrow there's a change in requirement that you need to do, you can click the state and make a change. You not only know what, you not only make the change, but immediately you are able to make an impact analysis, like what other requirements or what other behavior is going to change because of this particular change request. So a deeper impact analysis is enabled through such a modeling method. Okay. Next, I'd like to take you through the idea of connecting this. So I mentioned that these all have to be connected. These diagrams have to be connected. You have to animate and you have to make it dynamic and so on. So that's the emphasis. You need to do it. But how do I start? Should I start the behavior modeling first, or should I start the structural modeling first? It's not like a chicken egg problem. The idea is, if you are very well aware of the system, you can probably go with structural modeling. You know what are the building blocks, and you can start modeling those in straight away. But on the other hand, if you are very new to a system, it's better to understand the system better through a use case or an activity diagram, which is an early behavior modeling method. Now, the focus should be to create a banking strategy where the structure, behavior, and requirement are such that they enable seamless impact analysis. The other point is, how do we integrate model? So I have a model for, say, doors, I have a model for HVAC, I have a model for TCMS, I have a model for brake, and so on. Or within this, I have some models. How do we integrate the model? So integration strategy is also very important in creating an MBSE approach. Some techniques I would like to share with you today is, one is ontology-based methods. So ontology is like having the knowledge of things and relationship between things. We can also take the relationship from the lexical language and create a relationship and create an integration strategy. And it also requires a deep system thinking to be able to create a right integration strategy. You need to connect the parts to the whole. That's the idea of system thinking. Overall, meta modeling should be done before we start the modeling. So what is a meta model? It's a model defining the modeling process. It's a model about the modeling process. So I would suggest that you should all follow meta modeling before getting into action modeling activity. Okay. Next topic is on the decomposition strategy. So when a requirement comes to from an operator, it would be a very high level. And as it flows through the rolling stock manufacturers, it has to be decomposed into multiple layers. Straight away, it cannot be taken to a stage, it goes into a tier 1. So there should be partitioning of the requirements into various elements, and then it can be cascaded to the tier 1 level. That means there's a layered approach that is required. So here is an example approach that I can show you, which we have been doing. That is, there are 3 layers there: operational requirement modeling, functional modeling, and subsystem modeling. So what we do at operational modeling level, at this level, stakeholder needs are captured. All activities and operational modes are captured, active surroundings and all are captured. And we'll also do the virtual operation that you saw in the video some time back. To give an example, say, suppose customer has mentioned that ASDO functionality is required in the train, such that units shall be fitted with an ASDO such that only doors within the platform length is permitted to open. Now, operability modeling will ensure that the ASDO pattern is captured correctly, driver pattern is captured correctly, all the nuances of say when the pattern has to be cleared, all the alternate possibility, everything is captured very well in that. Next, at a functional modeling level. At this level, what we do is do a functional decomposition. Logical structure, the behavior, meeting the customer requirements is the important thing that is like what we are trying to model. Now, to give an example, why this is important, just think about the example of a braking solution. Just as an example, if you look, braking involves conventional train control, TCMS, braking, propulsion, and there's almost a 200 requirement. 200 requirements are required to achieve this. It's as complex as that. So things like, say, okay, traction brake control position is set by the driver, and then TCMS evaluates this and sends the signals to braking. A braking module receives the signals from TCMS, and then it calculates, say, the electromagnetic effort and passes it on to the ED braking and so on. So it's quite a complex system in itself. Okay. Now, all these 200 requirements working out in the head or in a textual document is not a right way. Modeling it makes it very correct, and we are sure that all the 200 requirements are complete and correct, and all the interfaces are perfect. Finally, on the subsystem modeling, here the functional modeling is at a logical level. Logical blocks are identified and logical level exchanges are defined. At a subsystem modeling, it comes to a physical level. You actually mention the actual physical bus or the physical cable through which the message goes. In case of say software, you can take as a physical signal like a CAD signal. In case of a mechanical, it could be say the piston. So in that way, you can also model the subsystem level. The important trait while trying to define layers is that there should be a clear context level, and each layer should be well abstracted from the previous layer. And the other aspect is there should be a transition from what to how. So when you start out, it will be the what at the operational level, and as you come down, it will be transforming into how. There's another common approach that many rail companies follow, that is the RFLP approach. Here it's 4 layers: requirements, functional, logical, and physical. Yeah, the layers definition is something that we have to do along with the OEM in understanding the OEM's problem statement and trying to define it. Okay, the next concept is on product-led engineering. PLE is a concept that's independent of MBSE, but MBSE acts as a great enabler for it. PLE or product platform-based engineering, what it allows is that the concept is that we have got 2 or more systems with some similarities. We should take advantage of the similarities and develop the programs together. So you can have one platform and multiple projects out of it. So initially there's a higher investment to it, but after a break-even point, there's a lot of advantages in this approach. So PLE is already there, but MBSE will be a great enabler because MBSE allows you to capture 150% model. That is, you model 100% of your current project as well as 50% for future variants, and it's easily scalable. Next topic is on traceability, which is also something that everybody is interested in. So this is because it governs the quality. Okay. So what normally everybody do is create passive documentaries saying that, okay, A relates to B, B relates to C through a traceability document. The idea should be the traceability should be active or should be inherent. So as you go on decomposing, the traceability should appear on its own. That's when you can do reliable impact analysis. And just weak links is not good. Links should be such that they are typed. So they're typed by behavior, like their satisfy relationship or derive relationship or allocate, and there are many more, but there should be typed traceability. Now, the interesting thing is when you have to talk about traceability and you have got so many layers, it's very much possible that each department or each layer is modeled through a different tool. Then the challenge of tool integration comes in. So tool integration, there are methods. It's not something that is like not solvable. There are a lot of methods for that. Say there's one consortium called OSLC, which is an open community for system engineering tools, and they provide REST API based specification, which system engineering tool providers can implement, allowing integration of tools. The other way of integration is XML metadata interchange. So it's an export. You can export, say, information as an XML data. Also, if you want to do simulation in parallel between two tools, you can use concepts like functional mockup interface. And finally, we are all working with SysML 1.6, and we are looking at SysML v2. And SysML v2 is around the corner, and that also brings in answers to tool integration. It is also defining a API at a SysML level itself. Now let's see how MBSE can be used for full-fledged deployment and how it can enable, say, left shifting of the entire V-cycle. So we saw a V-cycle earlier, right? In addition to that, what you have here is those green boxes. They are the virtual operation, virtual specification, virtual design. Now, what happens here is that at the moment operational requirements is developed, virtual operation model is used to test it. So it's like a test-driven paradigm. And the moment your functional requirements are done, your virtual specification for the function is executed and so on. So it's like a virtual train that we are trying to achieve here. And this is something that we are already doing. Now, TCMS, so I can say that it's definitely possible, creating something like a virtual train. Now, why is it useful? Just consider TCMS is a central nodal system, and you have it interfacing with multiple systems like the HVAC, door, brake, lighting, passenger electronics, and all. So let's take the virtual design concept. From bottom up, let me look. Say from the virtual design point of view, if I take the TCMS and I have a model which has all these interfaces, my discussion between the OEM and the tier ones will be so much better. The collaboration will be there. So as soon as the tier one delivers something, there's a virtual design against which it can be validated. Or in other words, the tier one has a virtual design as a specification to which it should align to or meet. So there it improves collaboration between the tier one and the OEM. At the top level, if you look, the virtual operation is something that can be used for agreeing the requirements between the OEM and the operator. So that improves the collaboration between the OEM and operator. Okay. Now, have you looked at the MBSE concept? Introducing anything will involve investment, and we need to look at the return of investment. So from market surveys and our own internal data, we can say that in terms of cost saving, we can get, say, 25 to 45%, and in terms of time saving, 35 to 55%. For the investment part of it, you need process definition, infrastructure, tools, and so on. On the gain side, we discussed on all those points like early validation, PLE for reuse, reducing the risk. It's a big item, that is complexity reduction, improved collaboration between stakeholders, and overall traceability. Next is, so we have done this. Okay, so I thought this could be an opportunity where we could share some lessons learned from our day-to-day deployment of MBSE. So we provide service of MBSE in three buckets. So the first one is process advisory. So what we do is go where organization hasn't or has a partial MBSE or has no MBSE process, we try to adapt or improve upon that. So in this case, the biggest lesson learned is that we should try to align to existing process. It's not that for deploy MBSE you have to redo the entire organization's current setup. We should try to align to it, and it's always possible. We can fill the gaps. For example, if an organization has an MBSE process where only structural aspects has been emphasized, we can put the behavioral aspects into it and interlink it well. So that is the lessons number one. Second is that there could be two approaches. One is the forward engineering way of doing MBSE, others are reverse engineering way of doing MBSE. So some customers prefer to take new features and do the forward engineering of it, or some cases all the legacy system are reverse engineered first and then a new feature is brought in. Both approaches are useful. And the third lesson there is that process should be the primary focus. What happens is in some certain, from the lessons learned is that if you focus on choosing an MBSE tool first and then creating a process around it, it might lead to issues. You will start struggling to realize the full benefits. So define the process and then move into the tool. Now looking into the tools part, given any tool, there will be limitations to align to the process that you would like to. So customization is inevitable. That is the lessons learned, and we provide that as a service. We provide, say, plugin development, continuous integration and continuous development. That is, as soon as you have a change, it should cascade changes or create emails and so on. And then creating custom profiles, etc. Finally, while doing modeling, which is the bigger volume of work, once you have the process and tools placed, what we realized is model should be such that you can use it for collaborating. If you create a model and shelf it somewhere, that doesn't help. It will be still a document. Model should be the primary means of discussions in the boardrooms or in any meetings. Second thing is simulation is something that is very useful. It brings in lot of advantages. Lot of issues are in through simulation. The next point is we can choose two levels of modeling. It could be a black box modeling or white box modeling. For example, from an OEM might ask a brake system provider to give the brake system information, but it could be at a black box level that OEM will get it. On the other hand, within the tier one, while modeling the brake system, a detailed white box analysis can be done. Reuse is an important lesson learned. Unless you're able to reuse, the benefits or the return of investment that we said earlier may not be achievable. So we should try to reuse as far as possible. And the last lesson is that language is always a matter of choice. So that can be negotiated. And here's an example of like our deployment journey. So it's not like we create the process in first place and deploy it across the organization. Deployment is not going to be working that way. From the lessons learned, we can say that there will be few early adopters who will, with small departments within an organization who will start using MBSE. And that will start reflecting upon the organization. And then there'll be MBSE in silos. Soon, there would be exchange of information between these system engineering teams. They'll start collaborating with each other through models. Eventually, it is something that will spread across the entire organization. So early adopters are the ones who led the organization's success. And it's not so difficult. As you see on the bottom, the language, the tool, all these are taken to a simple implementation is taken in the beginning. And as we go, the language extends, say only 10 or 15% of the constructs of SysML were used initially. But as we move to the right, more and more complexities can be introduced. This is the best way to get early adopters. Okay. Now we started off with focus on core modeling, okay, and realized that that's not enough to create an MBSE Center of Excellence. Now that we have that, I think I can share you that a lot of different skills are required. We need process architects, we need modeling language experts, you need design pattern experts, engineering tool experts, plugin development experts, and so on. So it's a cross-skill team that is required to set up a MBSE. So that's a lesson learned. I thought of letting you all know. The other thing is that there's a common concern which is raised everywhere. That is, system and domain experts prefer traditional methods, and modeling will fail without their contribution. So if the knowledge is not brought out, how will you model it? And while we discuss with visionaries, what we realize is that knowledge system is critical for the organization. So letting it in individual's head is not the right way. MBSE follows, MBSE models are the right way to capture the knowledge system of an entire organization. And whatever perceived apprehension is there that from the modeling engineer, from the experts, we can definitely mitigate it through training and active engagement. In fact, just before this webinar, I had an interesting case where one of our clients said he would not be able to join the webinar, but he said how MBSE models helped him. So what he said is that the entire knowledge system, which was built through MBSE over the last year, has helped him in the current pandemic situation. Otherwise, it would have been so difficult to discuss requirements or design. Now, with these models, they are able to do it with ease. So to summarize, on the left, I've shown some of the client excerpts from client testimonials. And on the right, I'm showing some of the word clouds. So these reflect the engineering benefits we jointly achieve with these clients. Okay. So by now, I hope you have been able to visualize that if a disciplined, holistic, and systematic approach for MBC is used, the overall outcome on a rolling stock project is going to be positive. And all that outcome is captured in the bottom of the slide. So this is also same thing that I set out in the beginning, the benefits, business benefits in the first slide and the challenges that we had to address in the second slide. I hope I've been able to summarize this through the session. So Martin, we are now open to Q&A session, please.
Sajan, thank you very much for that. That was excellent. Thank you very much. Okay, first question. Sajan, this is for you. Having worked in rail, aerospace, and automotive, how do you compare the adoption of MBSE in these?
Oh, that's a very interesting question. Yeah, indeed. Okay, so I'll start with the aerospace. So in aerospace, MBSE adoption primarily started off because to address the complexity. As you have seen in the slides that it helps you in mitigating the complexity, and aerospace has got a lot of complex systems involved in it. Complexity because there's a lot of redundancy in systems, and therefore modeling helped there. And there's another reason why it was adopted in aerospace a lot, because this is a systematic and disciplined way of doing your system engineering activity. And there's a stringent audit. There are tough amount of documents and artifacts to be produced to prove that you've done things systematically when it comes to aerospace. So that's about aerospace. Now, if you compare, say, to automotive. Now, automotive, the reasons were only probably on the complexity side. So if you look at a feature like the ADAS, with the emergence of features like ADAS or autonomous car, we are getting the complex systems inside the automotive also. And then the adoption of MBSE has happened in the automotive segment. On the rail, where we see is on the concept of platform reuse. So that is the primary reason for adoption of MBSE when it comes to the rail industry. Yeah.
Thank you very much. A question here from Salvatore. How do you manage the transition between textual, customer, high-level requirements into models, and how do you export model into diagrams, schemes, text document to be shared with stakeholders?
Okay. So I have tried to give an encapsulated view of the whole MBSE. So deep dive into how probably we can take it offline, but I'll give a quick idea. So what we do is take any textual artifact. There is enough information in that to capture the structural behavioral aspect, and we put it into the models, and we don't let go of the textual artifacts. They are going to be linked then and there. So you know from where the models have come up. And with use of proper tools, there are options to export these artifacts as well. So yes, it can be done. Deep dive into how, we can always take it offline.
Thank you very much. I've got another question for you all from Alan. Many organizations run both a paper-based system design methodology and MBSE. How would you recommend that the organizations transition from paper-based to full MBSE?
Ajit, would you take that?
Yeah, I think the best approach should be that we have deployed came from automotive industry. They looked at the um, entire system landscape and said that let's start with the dynamic functionalities to model, because the saving that you're going to get out of that is much higher, and because you're going to reduce the issues that will go out into the market. So uh, we would recommend that look at your systems in the landscape and pick up the ones that can give you the maximum impact in terms of your goals. And in automotive industry, it's the choice was dynamic systems like ADAS and autonomous technology, electrification. Those were the ones, and also the other point of view. One more point of view I would say is that if you're developing some technology ground up for the first time, not mature, for example, digital transformation of your trains, um, you should go for MBSE because this is a ground up development. This is starting now. So follow MBSE. That's because that's the right way to do it.
Thank you very much for that. Next question for you from Gregory. Firstly, great presentation, very enjoyable. My question is, while accepting there may be high costs associated with it, can the models be used beyond system commission introduction stage to better undertake change management over the system life cycle, especially noting the relative long use life of railway assets?
Absolutely. Yeah, absolutely. So I'm assuming that Gregory is working in rail industry, and he has the knowledge of change control boards. So when the change management happens, the change request comes into the change control boards, and then we do a triage of all the impacted parties. And during that triage, Sajan mentioned about collaboration, model being a tool of collaboration. So that's where the model really helps. You look at the system, and you can plug in the change and straight away bring out the impact that the change has on the surroundings of the system in a much better comprehensive manner. So you can reduce the manual efforts required there and take an informed decision based on that.
Thank you very much. Another question here from Ki Fang. Thank you for a very nice presentation. My question is, how do you manage specifically in the rail industry that the system of interest can vary for different train composition, coupling, uncoupling, etc., while for many other industry like aerospace is often fixed SOI and relatively close system like the aircraft as the whole itself?
So I'm not very clear on what exactly he's asking, but let me just try to rephrase the question there. So he's saying that aerospace is a much more controlled engineering environment as far as system is concerned, whereas in rail there is lesser control. Is that what he's saying?
I believe so, yes.
Yeah. So that's not our experience. Automotive, aerospace, and rail all have closed loop control systems and certain open loop control systems, and the definition methodologies are same. So what succeeds in aerospace can be successful in rail as well. Standards are different, so you need to adopt the standards. But as a methodology, you look at rail industry, look at the operational requirements from the customer, then create the activity use case diagrams and decompose it into functional diagrams, and then push it down into subsystems. So that's the process that we use.
Thank you very much for that. Another question here from Pierre. Do you start MBSE at train level or rather for smaller components? Do you find any interest in MBSE to components other than software?
Right. So let's break down this question into two parts. Number one is, do you start at the vehicle level? Ideally, yes, should start at the vehicle level. But if you recollect Sajan's presentation, he spoke about reverse engineering. There are scenarios, and we've done those. We've done similar projects where the customer has mature engineering products, engineering work products, and they want to re-engineer to introduce MBSE because they don't want to lose that knowledge. So yeah, so the journey can be up, down, from the vehicle to function to components, or down, up in the initial stages of introduction of MBSE. But once all the work products are in place, then you implement MBSE top down. Then it's ideal to implement it top down. And the second part of the question is, does MBSE play a role in non-software? Of course, all the dynamic systems can be a subject of MBSE. If you remember what Sajan mentioned, he mentioned about pressure gauge being an input device into the system. So it depends on, it doesn't matter whether it is a mechanical system or an electrical system. The core criteria is that if it's a dynamic system, it can be modeled, it should be modeled in MBSE methodology, ideally.
Thank you very much for that. Another question here from Augusto. How much time and people do you need to model train functions compared to the standard approach?
Right. So that's a very interesting question because depending on the function, it changes. So let's do a comparison. Do you want to take that question? If you compare creation of specification, or let me give that answer. So we developed hand-authored functionality document. It took us 4 months to develop hand-authored functionality document for one of the rail systems. For the same rail system, it took us initially 6 months to develop the model, but the subsequent variants, once it is developed for the platform, the subsequent variants did not take 4 months. It took about 2 months, 2.5 months, then came down to 1.5 months. So initially, why did it take 6 months? I think if you go to Sajan's presentation, he spoke about knowledge being inside the head of people. And there is a lot of stakeholder discussions involved initially to capture the requirements into models and then iterate it to make sure that the person's knowledge is captured within the model and archived in the library. So that process adds on to the engineering effort, but subsequently you start seeing the gain.
Ajit, I would like to add there that it also depends on the system. If you take a brake system, the benefit of MBSE might be different when you take it from a passenger entertainment system. So we need to, it will be system by system. The benefit or return of investment will definitely vary.
Yes, and let me also add that in addition to what Ajit and Sajan have said, I think the most important thing here is when you created a base, and then any change that you then make when you have a platform reuse, you get automatically the benefits of traceability, the impact analysis, which is what actually brings out the essence of why we go in for model-based systems engineering. Interdependencies are very clearly marked. You make a change, you don't get an unknown effect somewhere else. You find it out right at that system engineering level. That's the biggest advantage, which I would like to point out here.
Thank you very much to all of you. Next question. How do you manage variability and product line engineering with MBSE?
Okay, so I touched upon a point where product line engineering we can achieve through 150% model. So 150% model is something like you have the repository of models. You have concept of like configuration or a folder where you have all the library of reusable elements, and there's definitely going to be a configuration control for that in such a way that two projects can reuse that library, and and only the differences are modeled project wise. So It's through what would you do if you were doing it in a textual way? You would try to do a base component, and you would have to try separate textual documents for variations. That could be similarly, you will try to create a base library in this case, which is more effective, and variant-wise separate models.
Thank you very much for that, Sajan. Next question for you. How long have TATA ELXSI been using the MBSE system?
So about 12 years, we've been using MBSE system.
Thank you very much. Next question for you. Is this just an Asian customer base, or are you servicing, or can this be deployed globally?
Globally, yes. So we've so far serviced requirements in model-based engineering and model-based systems engineering from US, Europe, Japan, and in India and China.
Thank you very much. I think this is a question for Sajan. You talked about TE customer journeys. So with TE being a technology company, is there an MBSE focus for your internal R&D activities?
Okay. Yes, we are a technology company, and there are a lot of R&D work that we do. And while we do, say, for example, the TE's autonomous car is something that is quite famous now in the automotive sector. And we did use model-based system engineering techniques in our autonomous car journey as well, because it's so complex, and MBSE made it so easy. Yeah.
Thank you very much. Next question for you all. How long on average does it take to implement MBSE within your customer's design stage? Ballpark figure, weeks, months?
So within the rail industry, a typical product development lifecycle in a scenario of 60% carryover, 40% new function is about 18 to 24 months. That's the typical time frame to run through the V model from operability to homologation and launch onto the network. So we are the MBSE processes that we deploy are a different way of doing the same V model engineering, and we meet this timeline. Yeah.
Sandeep, did you want to add anything?
No, I think it is also a factor of many other organization parameters in terms of the maturity of the existing system engineering process and the culture of the organization for change. So in addition to the points which I alluded to, I mean, there are other aspects also which come into play, in terms of the timeline to get it started and roll it out across the projects.
Yeah, if the company is decided that we are going to go forward with MBSE and are ready to go, then yeah, it fits within the time frame that I just described.
Thank you very much to you all. Next question. Is your MBSE the exact same format process for each customer, or is it customizable depending on each specific project?
I think I did tell in terms of lessons learned that organizational process is a key factor when defining MBSE process. It's going to be in 100%. I can assure you that what you do it for one organization, you can not replicate it for the other organization. Yeah. There are so many parameters to it. Yeah. For example, the department structure itself. You will already have an existing department structure with an organization. You might have defined, divided into an operational engineering team, a vehicle engineering team, based on various systems you may have team. Now, I cannot go about saying that, no, my layer talks about having only 2 teams. Let's reorganize your department. That's not going to work. Rather, we understand what each department is doing, what is their day-to-day work, what's the input to their work, what is their output from there, what is their input, there's output, and what they cascade to the other team. And based on this, we try to work around the MBSE process.
Thank you very much. Next question for you. Can you highlight some real-life examples of the value added MBSE has delivered to customers? Can you name the customers? But I don't expect you to name the customers if you can't.
I don't think we will name the customers, but real-life value, Sajan, if you would like to take that.
The virtual train, as an example that I've told you, is something that we are setting up for some of our customers. And without naming the customer, I can say it has helped in multi-level. From an operational perspective, the operational requirements are much better today. from the subsystem perspective, a lot of issues from the subsystem level have been captured. But I wouldn't go about defining or giving an example from a customer project due to the confidentiality concerns.
No, totally understand. Thank you very much. Next question for you. Can you please give some examples of tool chains used to enable entire MBSE process in rail domain?
Okay. So if I name out two tools, it might seem I'm biased to the tool. So I would try to keep it as tool agnostic, the MBSE. The slides in this presentation are giveaway about some of the tools that we prefer, but then we have worked with, I think when you saw the slide on our COE, Center of Excellence Competency, we did cover tools like Magic Draw, IBM Rhapsody,
Control build.
It's a control build, and it's not limited to those, but just to give you a flavor that we work on.
These are the big three that we have come across.
Yeah.
Thank you very much. Another question for you. Does TATA ELXSI provide a repository of reusable models? Can we get reusable model for brakes?
That's an interesting question. So we do modeling as a service to our clients. So if a brake manufacturer wants to do a modeling, yes, we do the brake model, but that cannot be reused for another customer. We maintain the data integrity, and it's restricted to that customer who has given us the project. Only thing that you can carry forward from one customer project to other customer project are best practices and lessons learned. You won't get the models as such.
Thank you very much. Next question for you. MBSE is reusable between the OEMs?
Between the OEMs.
Okay, if I can take that. Between the OEMs, typically, I mean, an OEM, doesn't collaborate with other OEM when it comes to, building trains and, launching train projects. So the short answer is no. But the interface of one OEM with the operators, as Sajan has already alluded to, MBSE is already being used even by operators for the operational and the maintenance phases. So so that is the answer. But between OEMs, I don't think so that they will be collaborating, except the MBSE approach and a methodology which can be shared.
Thank you, Sandeep. I've just had somebody write, may we have a copy of the actual PowerPoint today? You can see Sajan's email address there. If you'd like to drop him an email, I'm sure Sajan will come back to you and let you know if they're allowed to give a copy of the presentation. So his email is just on the holding slide there. Next question for you all. How many engineers and/or effort is needed to migrate from the traditional approach to MBSE approach, considering all the functions of the train?
All the functions of the train. We are currently doing a project, but again, depends on the maturity of the customer. This particular customer started thinking about MBSE back in 2015, laid down the processes, and after about 2.5 years, we started working with them on MBSE. So the effort is 320 person months for the platform level definition of models for all functions of the train.
Thank you. My apologies. I was just reading something else, another question. Another question for you. Importance of binding behavior, structure, requirements is well understood from the session. Will this be able to capture numerical and other measurable factors that defines the system? For example, permitted tolerance of a system, maximum axle load, etc.
Yes. So for ease of understanding and to give you the emphasis of binding of structure, behavior, and requirements, I did skip the fourth pillar of say SysML. SysML has actually got 4 pillars apart from structure, behavior, requirement. We have a 4th pillar called as a parametric. We don't use it everywhere, so that's why it's not omnipresent, and that's why it is not in that slide. But let me explain what parametric diagrams really help in. So suppose you have a block and you have say 2 ports as an input, A and B, and the third port is C. It's mathematical equation C is related to A and B. Now, what parametric model helps is in knowing, like, when I change A and B, how the value of C will change. Or if I want to keep C as a constant value, what should and if I know A, what should my value of B be? It looks very simple with just a block with A, B, and C, but this can be done across the entire system. So if you have parameters defined for every block in that internal block diagram and entire system connected, you can imagine, like, just fine tuning a parameter, how it affects the entire system. You can study it, and that's called parametric modeling.
Thank you very much for that. Okay, final question for you. Do you only provide your MBSE design and engineering services to other sectors outside of rail? If yes, which ones, please?
Automotive and aerospace. Outside of rail, we provide for automotive and aerospace.
Okay, many thanks. In fact, I've just got one more question for you, which I'm going to ask.
Sure.
Please, can you provide some examples of those cost savings achieved via your MBSE graph slide 21? I appreciate there will be an initial investment, but it would be helpful to know how long-term saving achieved in real statistics, if possible.
Right. So,
Ajit, the
can
challenge.
Sorry, can we respond to that later?
Of course.
Yeah. Okay,
whoever's written that question, please do drop Sajan an email, and he'll come straight back to you with an answer for that one. In fact, I've just got one final question. Here we go, from Jason.
Sure.
MBSE appears relatively theoretical. Whilst it appears quite robust in structure, does it translate to actual operation? And have you experienced any gaps in expected system behavior due to the operational environmental infrastructure factors in particular?
Right. So the first part of the question says that it is quite theoretical, which is not the case. It is quite practical. It has been practiced actively in aerospace industry, then automotive, and now in rail. We have live projects running in rail industry, and we're delivering projects to the end customer on MBSE. So it's very live. And can you please repeat the second part of the question?
Yes, 1 second. Let me just get it for you now. How does it translate into actual operation, and have you experienced any gaps in expected system behavior due to the operational environmental infrastructure factors in particular?
Right. So the operational aspects of the project gets defined at the early stage of the project at the left top of the V model. So the operability requirements across all operational modes are defined first. And then that forms the basis of downstream engineering for MBSE. It starts, the operational requirements are defined as activity diagrams and use case diagrams, as Sajan mentioned. And then that is the start. From that point, we then go down through the V model to define the downstream work products in MBSE. So that is factored in. That is the starting point, and it is factored in to the whole process.
Thank you very much. Sorry, Sajan.
Just one point. When someone asks me, like, can you say list of issues that were solved because MBSE is there? I find it very difficult. Just because when you do MBSE, the issues aren't there. So what issues might have been there when there is no MBSE, it's a hypothetical case. So just because you use MBSE, you'll realize that there is no issues later. And if you have to really compare, you have to compare against program 1 versus program 2. And how many programs or issues were detected in one program and how many are there in the second one. It's just to say that I've used MBSE and then I identified these issues. Well, I'm doing systematic method, and that's why issues are not coming up.
Thank you very much. Actually, I've got one more question here. So you've done so well. This is going to be 24 questions you asked. So I'm going to ask it. Do you have an association between MBSE and rolling stock asset management during your train testing?
Rolling stock asset management. What's the last part? Sorry.
Do you have an association between MBSE and rolling stock asset management during your train testing? Apologies.
No, we've
No.
not. No.
Rolling stock asset management is part of the, once the train goes live in the operations, we are talking about the asset management from the operator perspective, from maintenance perspective. And here, I think in today's scope of webinar, we talked about MBSE for the design development phase. So these are two separate phases of the vehicle.
Thank you very much for that. They just said thank you. So I think you've answered the question for them. Sajan,
Okay.
did you want to move on to the next slide because you wanted to say something?
Sure. I would like to thank all the audience. Thanks for all the interesting questions. Thanks for listening to me patiently. We look forward to host another webinar. It's up on the BREL website. It is scheduled on 16th of December. It's about passenger experience design. Yeah, so that's what I want to say. And I want to just again repeat, thank you all.
Thank you.
Thank you very much for that. Ladies and gentlemen, I would like to say a big thank you to Sajan from TATA ELXSI for an excellent presentation today. And thank you to Ajath, Sajata and Sandeep for being panelists. You were superb. You've answered over 24 questions. Absolutely superb. And I thank you very much. Ladies and gentlemen, today's webinar will be on demand for you to all rewatch. It will be uploaded onto the WeRail website ASAP. Once again, thank you to everybody for attending, and a big thank you to the speaker and the panelists from TATA ELXSI for a wonderful presentation and Q&A session. We look forward to seeing you all at our next WeRail webinar. Thank you all. Have a good day and good evening. Goodbye.
Goodbye.
Bye.